welcome to the directions video for Lab 13, which is all about the Hertzsprung-Russell diagram, which itself is about properties of stars. So in this directions video, I'm going to talk all about the lab itself. Basically, I'm going to show you a lot of the links because there are many links in this lab to lots of different web pages. Make sure that you get an idea of what you're expected to do with those different pages, how they tie in with the actual questions that are being asked. I'm going to give some examples of the calculations, of which there are a few different sections, and just a general idea of how everything ties together. And I'm going to do that by going through each of the questions. Okay? So I went ahead and looked at part one, which is key terms, as you can see here. And I've clicked on the first link. So you can see it's already open over here. And this first link is a wonderful website that has just lots of helpful information, and everything is kind of linked like a Wikipedia article, but it's very user-friendly and is at a good level in terms of introductory astronomy, whereas if you go to Wikipedia, you can get some very advanced information, and it might become a little bit overwhelming. But here, right, you can see that this the link here is about the Hertzsprung-Russell diagram itself, which is often called the HR diagram. We can learn that it is one of the most important tools in the study of stellar evolution. And I guess I should mention that, right? So if you think of the periodic table, which shows all of the known elements, that's a really big deal for chemistry, also for physics. It's such a main document, a wonderful reference. Well, the HR diagram is something of the equivalent, but for astronomy, right? So it's just one particular figure that tells so much information all in one. Now, of course, sometimes you can have too much information in one figure, and maybe it's better to split that up a little bit. But when it all ties together, you can see the big picture. You can see the connection between ideas. And indeed, here it is. Here's the Hertzsprung-Russell diagram, the HR diagram, and it has 4 axes. So how is that possible, right? You think of a typical graph that has 2. Well, that's because each of the horizontal and vertical axes, so horizontal and vertical over here, are serving double purpose. So the horizontal axis, as shown up here on the top, is temperature, but it's also simultaneously spectral class. That's because spectral class equates to particular temperatures. These are the surface temperatures of stars. Everything shown here are stars, okay? On the vertical axis are two scales: absolute magnitude, which is represented as uppercase M, with often a subscript V, which I use consistently throughout the lab. At least I hope I use it consistently. And then luminosity, and which is actually here normalized or measured as multiples of the luminosity of the sun. So it's all like factors of how bright or how luminous are these stars relative to the sun. And within the diagram itself, we can see that there are groupings of stars that are kind of colored here. So there's this big swath of stars across the middle, which is called the main sequence. That's what's considered a type 5 star. So in addition to spectral class, there are types of stars: white dwarfs, as I already mentioned, main sequence, giants, subgiants, supergiants, even hypergiants. There's a particular famous part of the HR diagram called the instability strip, which relates to these things called Cepheid variables and other types of variable stars, which have their own importance, which is not covered here, but you can just see that there's so much here. Stars and the way we classify them and understand them is crucial to understanding the cosmos itself, because they are our landmarks, our benchmarks, our signposts that we can measure distance relative to and figure out how far away things are, how old things are, all about understanding the evolution or life cycle of stars, okay? And just how they group together. So, what's the first part about? Well, key terms, all right? So you've got all these terms. I want you to look up definitions to them within this webpage. Now, you could go anywhere on the internet and find lots of information. You could, crack open an astronomy textbook, but I figured this would be a one-stop shop where you can find definitions like brightness, luminosity, absolute magnitude, apparent magnitude, spectral type. Okay, I mentioned that. Which is different than spectral class. Then you're going to specifically look at the Hertzsprung-Russell diagram. You're going to have a definition for it itself, which I kind of already mentioned. Then you're going to talk about the main sequence, which is one of those spectral types. Okay, red giants, white dwarfs. Okay, so there you go. You got one page of key definitions. Many of these, or basically all of them, will come up again at some point in the lab itself, so it's going to be helpful for you to have a good upfront understanding, or maybe as you go along, they'll make more sense. Okay, like what the heck is the difference between absolute and apparent magnitude, right? Because it's not that apparent right away. Like what's one? Why are there 2 definitions that look so similar? Okay, so another website that I want you to go to is this link right here. Okay, Now, this is part of a group of astronomy simulations. This is one of their background reading. If you've looked at any of my previous labs, and you know that these often come up, right? This is the University of Nebraska. This is their NAP labs. Okay, and here I decided to go to this website, not because you probably couldn't find the information here, but just it was so readily apparent at this particular site. And the information I want is basically a definition or explain the meaning of the Stefan-Boltzmann law. So if you look here, this is basically a background on light, which is the study of light is often called spectra, because light is all about this idea of falling on the the electromagnetic, spectrum, all right, which ranges from the highest energy light to the lowest energy light, which, by the way, is all the way from gamma rays to radio waves. You have important laws like the speed of light and how it relates to the wavelength and frequency of light, the electromagnetic spectrum itself, shown with common sources, both terrestrial and and less terrestrial, more exotic. Then relating the concept of intensity and sources of light, and where we see intensity peaks, which are kind of a fingerprint of what is creating that light. Very important for scientists in general, but especially astronomers. They can look out into space and just look at particular wavelengths and figure out what things are made out of, right? So what's the composition of stars, or even the composition of exoplanets, let alone the composition of objects within our own solar system. Here is the emission spectrum of hydrogen. Emission spectrums are a type of the signature, and in fact one of the more specific ones. They're in contrast to other types of spectra, such as absorption spectra, or another type called black body, right, which is a continuous spectrum. So instead of just particular bright bands, it's a big curve. In fact, here is a black body curve, all right? So it has a peak that is directly related to a temperature. That concept, that a peak emission, which is measured here in wavelength you can think of as kind of the color of light. So the fact that we have a peak emission at a very particular wavelength, a very particular color, and that corresponds to a specific temperature, well, that's of wonderful utility, right? Because when astronomers or anyone looks at a particular object, sees what color it's glowing, then they can say, this is how hot it is. And so objects that are very hot will glow in the ultraviolet. Objects that are a little less hot will glow blue. Objects that are cooler still might glow like green or yellow. As they cool down, they glow red, okay? So you think red hot, well, sure, that's hot, right? But that's not the hottest of hot. As things, move, up the rainbow, they get hotter, blue being the hottest of the visible colors. And then when things are cooler, then they're actually going to glow in the infrared. That's like humans, for example. We are emitting light, our skin is glowing, but it's glowing in a wavelength of light that our eyes can't see, which kind of makes sense. Otherwise, you'd probably be blinded by all the glowing light around, and we wouldn't be able to discern the more important reflected light. But regardless of that, what we have is the idea that that peak wavelength, it's a very long wavelength, correspond to a temperature of around 300 Kelvin, in contrast to here 12,000. I might have said 1,200, but it's actually 12,000 Kelvin. Well, the point is that that's a much longer wavelength, much lower energy light. But how does this all tie in with Stefan-Boltzmann? Well, Stefan-Boltzmann isn't the law that directly relates temperature to wavelength, although that is quite interesting. That's actually called Wien's law. The law that I ask you to define here is the one that's represented right here with equations or with variables. It says F equals sigma times T to the fourth. Okay, F represents the flux. Okay, now this is it goes by many names, also known as intensity. Okay, a later part in the lab, I mentioned some of its names. It actually has units of watts per square meter. All right, so it's basically power per area, and power itself, wattage, is energy per time. So you can think of flux, electromagnetic flux, or just energy flux, as energy per time per area. Okay, so that's what F is. And the idea is that this amount of energy coming off the surface of any object, in this case we care primarily about stars, is going to be proportional to temperature to the fourth power. So in other words, as temperature goes up, you get a lot more energy coming off of the surface of that object, okay? And in astronomy, it's primarily stars, right? So this is a really strong relationship between the amount of energy that's coming off of a star compared to its temperature, okay? It goes shooting up, because raising something to the fourth power has a big effect. Like 2 to the fourth is it's 16, right? Well, 3 to the fourth is it's a huge number. I can't even think of it off the top of my head, but it would be, I guess, 81 cubed or something, so or 81 squared, so it's a very large number. The fact is that, that they increase really dramatically, right? Just, in that case, just going from 2 to 3. In fact, I have Desmos open so we can see how dramatic an effect raising something to the fourth power is. So if I take 2 to the fourth power, that's 16, as I said, but 3 to the fourth power, oh, that is 81, okay. So it's not 81 squared, but still, right, big difference. And then if we go to 4 to the fourth power, right, it jumps up even more, right? So these are huge steps we're taking, even though numerically we're just going from 2 to 3 to 4, right? So, you can see what we say is a strong dependence on temperature. Intensity, flux, has a very strong dependence on temperature. Now, that would be what's called a proportionality, except it becomes an equation because of that little letter right there, that Greek letter, sigma, because that's the Stefan-Boltzmann constant. Essentially, it's an empirical constant, which means a experimentally determined constant that ties those two quantities together. And it is equal to 5.67 times 10 to the negative 8, it's a small number, and then it's got appropriate units, right, to make it an equation, and that, of course, makes sense in relation to other laws and so on. Okay, so that's what I want you to describe here in number 3. All right, so part 2 is all, I didn't give it a title, but it's all about actually looking into apparent brightness, absolute magnitude, and intensity, kind of relating all those ideas, okay? It's a bit of kind of an aside that is going to take us away directly from talking about the HR diagram, but kind of understanding some of the underlying concepts, and then at the last part of the lab, we'll kind of bring it back to the HR diagram. Okay, but to remind ourselves that we are talking about it, I did include a little bit of background and a link to a really neat, basically another like a simulation or just sort of a, what do I call it? Oh, an interactive version of the HR diagram. And here it's useful, it's kind of neat to look at, but actually, like I said, it will come back front and center at a later part of the lab. But here it is, right? Here is this interactive HR diagram. So this is the same diagram that was on that Cosmos website over here, right? So this is this, diagram, shown here with some shading to represent the different colors, because essentially stars that are over in this section are blue, hence the blue shading. Stars in this section are red, right? So that's, this is a great way of showing it. It's very useful, and a lot of versions of the HR diagram look something like this. But a very different way of showing it is with a background of stars, like, kind of make it look cosmic, and then so just all black and white, or rather black and green, because we've got the same axes, or at least we have some of the same axes. Because notice that instead of having spectral class, we just have temperature, so we have one of the two horizontal axes, and instead of having absolute magnitude and luminosity, we just have luminosity, okay? And this is luminosity measured in luminosities of the sun. So this little symbol right here, L with that subscript, which is a dot with a center inside, that actually represents, it's a sort of a standard variable that represents the luminosity of our sun. Okay, so our local star, our sun, its luminosity is a unit in a sense, right? It's like a baseline measurement that we compare any other star to. Okay, likewise, we'll talk about this later in the lab. This interactive version of the HR diagram also has radii measured in base unit, so a base unit of the radius of our sun. So a value of 1.0 would be our sun. In fact, that's where the diagram defaults. When you first load the website, it shows the sun, and therefore the current value, it has a luminosity of 1.0 since it is the sun, and a radius of 1.0. Now these aren't in standard units, right? Because standard units of luminosity, as I mentioned before, would be watts per square meter, and standard units of radius would be either meters or kilometers, strictly speaking meters, right? The sun has some 10 million meters or 10 million kilometers, excuse me, for its radius, right? So that's its actual value. But here it's more of like a multiple, right? It's an alternate standard unit. And we can, the interactive part here is we can click on our object and move it around, right? So it comes out from behind the sun, and now it, of course, no longer is the sun. We can move it to different sections and actually see it change in color and size. That's pretty cool, right? So we can bring it over here and get it to be blue and fairly large up in the far left-hand corner. We can bring it down into a region that is actually where the white dwarfs are, which is one of the labeled types of stars on the other HR diagram on that Cosmos website. Bring it back up to the main sequence stars, okay? Bring it all over here. All right, again, you can, if you bring it far enough the main sequence, it becomes blue, and then everything over to the right of the main sequence, those were where the giants were, the subgiants, the supergiants, and so on. Right? Whoa, look how big it can get. Right? And then we can actually go back down to the lower right-hand corner and have main sequence stars that are small and red. Okay, as opposed to large and red. Those are some of the fun ways you can interact with this version of the HR diagram. Now, one of the first things we want to point out is that this HR diagram has, as did the other one, has a horizontal axis that is a logarithmic scale for temperature. Okay? So how do we know that that horizontal axis is a logarithmic scale for temperature as opposed to a linear scale? And what the heck is the difference? Well, let me tell you. Okay? So a logarithmic scale is basically factors of 10. So it's like a base 10 system as opposed to a linear scale. If you were to look at a graph that shows a logarithmic scale with some of the finer tick marks, you can see, for example, values that range between 0.1 and 1 are evenly spaced with values that range between 1 and 10. Clearly, that's not a linear scale, right? Otherwise, we'd have to, the even spacing would be between, 1 and 2, right? So this, we could have a 1 here, or maybe we could have a 1 here instead of a 0.1, and then the next mark would be a 2, and then a 3, and then so on, right? Like that's like a ruler, for example, a meter stick, a measuring tape, right? All of those have linear scales. And so if you were to look at some value that's between, say, 1 and imagine this is 2, halfway in between would be 1.5. But that's not the way logarithmic scales work, because they scale up with, with exponents, right? And of course, the inverse function to exponents are logarithms. And so what we have here is a nonlinear scale. So, 1's here, 2 is here, right? 3, 4, they get more clustered together, and then we get up to 10, right? Same thing when we went from 0.1 to 1. So the even spacing are all powers of 10 rather than additions of 1. All right, so that's a logarithmic scale. We can tell that the temperature here is in a logarithmic scale because look at the spacing. There's about even spacing between 5,000 and 2300. Okay, this all being in Kelvin, the standard unit of temperature. Okay, and you can go back and forth between Kelvin and Celsius. The difference is only 273. So honestly, when you get up to really high temperatures, like tens of thousands of Kelvin, it doesn't really matter if you're using Kelvin or Celsius because remember that difference is only 273. But the important thing is that both Kelvin and Celsius have a delta. They have a change that is the same. So if I go up 1 Celsius, I also go up 1 Kelvin. But anyway, that's an aside, neither here nor there. What we care about is just our scale here, which is in Kelvin. Okay, standard unit of temperature. So, but look at this next segment, right? When I go from 5,000 to 10,000, that's the same, right, scale on this graph, right? It's the same actual distance on the screen to go from 10,000 to 5,000. But that's not the same distance, not the same absolute distance, right? This was a linear scale, then this should be like 7,500, right? 7,500, right? Because that's about how, the gap here was 2,700, right? So this next gap, I guess, would bring us up to 7,700, but it doesn't, right? And then look at the next one. The next one goes from 10,000 to 20,000, right? So they're not exactly factors of 10, but they're a multiple of a logarithmic scale because you can have any base essentially, okay? Or just some multiple within the logarithm. And so here, right, then we doubled again, right? So we're doubling each time rather than going up in a linear way, okay? So then that's the idea, and to get a little handle on the differences, you're just going to do some quick calculations. So we have here is the first example is a type G star. You're told that type G stars, those are one of the spectral classes. Remember, those are the letters that showed up on this HR diagram and which are visible on many types. You can see you got types from M to K to G to F, A, B, and O. So O is the hottest, B is the second hottest, A is a little bit cooler, all the way down to the coolest stars, which are the M stars, right? Still pretty hot, right? But they're the coolest of the stars. Well, so here you're given a range of temperatures in Kelvin that a G-type star can have, which is between 5,200 and 5,900, and you're just going to take the logarithm of each of those. So what does taking a logarithm look like? Well, I did one here. I have it filled in. So for example, a spectral type F star has a surface temperature in Kelvin. I should have put the units there. Bad me. But a surface temperature of 5,900 Kelvin. Well, what does that look like as a logarithmic value? Well, you would go over to Desmos. I'll do this one as an example. And so I'm just going to take log, and then I'll put in the number of 5,900. And we see we get the value that I have already entered, 3.77. So you can see where I got that number from. So to calculate all these others, it should be very straightforward. It's just going to be log, which is a basic function built into something like Desmos or any graphing calculator, just about any calculator. And you just type in the temperature and then put the output here. So straightforward exercise, but what I want you to notice is that when you have these numbers, right, these numbers then are going to have a different sort of relative scale to each other than these temperatures did. So that's to just probably give you some hands-on experience with what a logarithmic scale is all about. Okay, so now we're going to take a look at some other ideas, which is primarily absolute magnitude, luminosity, spectral class, and temperature. And first of all, you're actually going to find the star Sirius, and I've reproduced the HR diagram that's the same as the one back from that original website. Okay, so that higher resolution, as you can see. And what we're looking for is just the star Sirius, which is one of the few labeled stars. Right? There's a kind of a few famous stars that are included here as sort of reference marks. So Sirius is a main sequence star. It is quite a bit up the main sequence from us. So what does that mean? Well, think about it: temperature, right, and then this magnitude, luminosity, right. So definitely brighter, right, because it's a higher vertical, and you can see as you go up with luminosity, you get more, brighter stars, right? More energy per area per time. And check out what type of scale this vertical luminosity scale is. Yep, it's logarithmic, right? It shows up a lot. A lot of things are when we talk about astronomy, because there's just such big ranges of values, it makes sense to have them in logarithmic scales. But anyway, you're just going to read off these four quantities, which are the two vertical and two horizontal axes, and just report them by looking at Sirius, right? Maybe you want to use a ruler to get some straight lines, but you're just going to be reading off the values from the chart, or from the figure. Okay? So then on to our next question here. Now we're going to navigate to basically an appendix in the OpenStax astronomy book, which is a great reference in terms of actual textbook and introductory to astronomy. Maybe some of you have used it in a lecture introductory astronomy class. So we'll go ahead and click on this link. Unfortunately, when you click on it, it doesn't want to work because it's taking the last part of the title. So you have to actually go and delete the last few words, probably depending on what sort of PDF viewer you're seeing. But I'm going to bring this down so you can see it. But you can see that it took some of the words after the period rather than just the link itself. I'll show you back over here. So you can see that the next sentence starts with find Sirius. But then when I clicked on the link, it's actually trying to include the word find. So I'm just going to go ahead and manually delete that, as well as the period, and then just re-navigate over here, and that'll actually take us to the right place. So here we are in the appendix of this open source textbook, and you're asked to find Sirius, okay? Because we were able to read some great information, in fact, 4 important data points about Sirius right off the HR diagram, our one-stop shop, our equivalent of the periodic table, but for astronomy, but doesn't tell us everything. One big thing it doesn't tell us is distance. Okay, now measuring distance is a huge deal in astronomy. We have there's just a whole history there and a whole series of techniques that astronomers use. In fact, one of my other labs is all about exploring the techniques that astronomers and the discoveries astronomers have made in order to actually measure distance, okay? Because how do you do that? You can't just, fly out to other stars, right? They're impossibly far away, in terms of actually getting there, right? So how do we know for sure how far away they are? But this is a collection of that information rather than a history of the technique or an explanation of the technique, because right here in this table, we actually see the distance, okay? So we just look up Sirius of all these famous stars. These are the brightest 20 stars, of which Sirius is one of them. And you're just going to read off that table the distance in light years, okay? And you're also going to want to convert it to parsecs, which, let's see, so it's not listed in both, I don't think. So we got luminosity, spectral type, yeah. So you're going to want to do the conversion. I thought I actually had a reference to the conversion, but maybe it didn't make it into this final draft of relating parsecs to light years. I'm just scrolling down to see if I mentioned it in another part. Because there's a certain number of light years in every parsec. A parsec is longer than a light year. Parsecs are a very important unit, and they're relevant in a lot of the equations we use, a lot of calculations we use in astronomy. They aren't as kind of the fundamental unit of distance that we see as much. Light years have kind of replaced them as the most common way we talk about the distance to anything, including stars in our own galaxy or other galaxies or any, all the distant objects in the cosmos. So but they're both still very relevant. Okay, so let's go ahead and just I'll remind myself of the conversion. It's about 3.2 light years per parsec, but I didn't put it in the lab itself. So let's go ahead and just do light years to parsec. Google has all kinds of conversions, including this one. All right. So we have 1 light year is 0.306 parsecs, because parsecs are longer. Or another good way is to find out how long 1 parsec is. It's 3.26 light years. So whatever you read off from the table, going back over here, for the distance to Sirius in light years, which you can just directly report, you also want that distance in parsecs. Why? Because that's the distance you need in the very next formula. So these next few questions are all kind of going, like I said, to this sort of side topic of understanding some of those quantities on the axes of the HR diagram, right? Because we've talked a bit about the temperature and how it's not a linear scale, and that didn't really get too much into the spectral class. It's just a way of grouping temperatures. But what's going on with those vertical axes, right? One's luminosity, one's absolute magnitude. What does that mean? So that's my goal with these next few questions. Questions 4, 5, 6, 7, and 8 are all about that. And then question 9 kind of brings it right back to the HR diagram. And then we're going to be done with some of these calculations. But let's take a look at what these calculations are all about. Well, the first one here, I say, is as explored in the key terms, right? Because you've seen this before, up in question 1. Absolute magnitude and apparent magnitude are related by the distance with the following formula. Okay, so the key idea, the key concept that separates absolute magnitude from apparent magnitude is distance. Okay. So I'll continue reading. Here's the formula, by the way. So it's a arithmetic difference. It's just one quantity subtracted by the other equals 5 times the log of the ratio of distance over 10. Okay, so that's how you use the formula. I'll show you an example. But we have here that I want to just identify our variables. So uppercase M with the subscript V is the absolute magnitude. That's the one we can read right off of the HR diagram. Okay, because the HR diagram does not have apparent magnitude. All right. Now it could, and you could probably find some version of the HR diagram that is instead scaled in apparent magnitude, but the standard is always to use absolute magnitude. Okay, and then D is the distance to the star in parsecs, not light years. If you plug in light years, you get the wrong answer. Okay, so we're going to use this formula to solve for the apparent magnitude. Okay, of Sirius. Okay, so use solve MV, which is apparent magnitude. Okay, so let's see. So you're gonna read it off, right? So I guess here I don't make it as obvious as I should have. Sorry about that. But we are still talking about Sirius. Okay, so on this one, because otherwise you don't have other than just to choose some apparent magnitude. But the idea here, absolute magnitude, because that's the one you read off the HR diagram. The idea is that you're continuing to explore Sirius. Okay. So you're going to plug in the value that you would have written down right up here, because remember you just read this one right off. Okay, so you have some number for the absolute magnitude off of this very figure. Okay, and then you'll plug that into that equation, and then you're going to solve for this lowercase m. Okay, because the lowercase m is the apparent magnitude. Now, I'll just quickly say, although you probably would have looked it up and hopefully had some understanding about what the difference between these two magnitudes are. Well, absolute magnitude is kind of a funny one. It's how bright a star would appear at a fixed distance of 10 parsecs. So it's like if you could take a magical spaceship, I say magical because the real, even in the most futuristic spaceship, sci-fi sort of spaceship, it would still take years or decades to travel between stars, right? In the very best case. Currently, it would take thousands of years to travel between stars with their current technology. But I stray into other topics. So, but the idea is, if you could get yourself 10 parsecs, so about 30 about 36 light years from any particular star you want over the vast swath of our galaxy, let alone other galaxies. Our galaxy itself is about 100,000 light years across. Well, so you could go there and you could position yourself there. This is how bright the star would appear. That's what absolute magnitude is. So it's taking the idea that every star would be this bright at this same shared distance. Okay, I don't know why it's 10 parsecs, other than that 10 is a nice round number, but that's the idea. Okay, so it's absolute because it's the same distance to all these different stars. apparent magnitude actually accounts for distance, because stars that are closer, even though they might be less bright, right, they might have a lower absolute magnitude, so because if you're close to them, they'd be relatively dim, right? But they also happen to be close to us, because there are some stars that are less than 10 parsecs away. Our closest neighboring stars are only 1, 2, 3 parsecs. There's a few dozen stars within 10 parsecs from Earth. So we have like a local neighborhood of stars. So those stars actually appear fairly bright in the sky, even though their absolute magnitude isn't that high. We're close to them, right? And the whole idea is that light decreases in intensity the further away you get. Just like on the surface of Earth, you get further away from a source of light, whether that's like a flashlight or a fire, you notice it dims with distance, okay? So that's the very idea we're talking about here, all right? So this is that formula to relate those two ideas, apparent to absolute. Okay, so I don't want to solve Sirius for you, because that's the calculation I want you to make for number 4, but I do want to do another example, so just so you can see the steps. So let's take a look at one that I don't ask about. Let's go ahead and do Vega, which is 25 light years away. All right, so let's go ahead and we know that the conversion is 3.26, so I'll go back over to Desmos. I'm going to put in 25, what was the exact number? It was 25.04, okay? So that's the distance to Vega in light years. I'm going to divide by 3.26, if I remember that correctly. All right, we'll stick with just 3 significant figures, although we have 4 on the other one. So let's add one more over here, 3.262. Okay, if I round up, because the 5 on the next digit would round the 1 to a 2. Okay, so then the distance to Vega in parsecs is 7.67. I'm going to call this D. Okay, Desmos is good about labeling variables like this, which can be very useful calculations. And then I want to actually calculate my apparent magnitude, which means I need my absolute magnitude. Hopefully Vega is one of the ones on the chart, or maybe I chose badly. All right, let's do another one that's actually on here. I thought Vega is a pretty famous one, but for some reason this particular HR diagram doesn't have Vega. So let's go ahead, and I asked about Betelgeuse later on, so I don't want to give that one away. And I don't want to do anything too close to Betelgeuse. So let's see if we can do, here's a fun one, Aldebaran, which is also very fun to say. So considering Aldebaran, sounds straight out of a science fiction movie. Is it actually one of the brightest? That would be helpful, wouldn't it? It is, good. So it's 66.64, okay? So the only difference here is I'm just going to put that value in instead. Okay, so 66.64. Okay, so now we have the distance to Aldebaran in parsecs, okay? Now I'm going to read off the absolute magnitude, not the luminosity, okay? Talk about that in just a minute, but the absolute magnitude, okay? So imagine, I'll draw like a vertical line. I can kind of wing it here. Okay, good. So I get an absolute magnitude that is, it's going to be positive, because you can see that as we go up, they become negative. So bigger ones are negative in terms of, brighter. Smaller ones are actually positive. That's interesting, right? Well, that's indicative of the type of logarithmic scales we're working with here. In fact, apparent magnitudes work the same way. Hint, hint. Okay, so we're above 0. Okay, because we're down, which is the positive direction. And I'd say, looking at it, maybe we're about 1/5 away, so probably 0.2. Okay, so I'm going to say 0.2 is my absolute magnitude. So I'll call that m sub v. Okay, so 0.2, save that in Desmos. Go back over to the formula, okay? So what do I have? I have basically everything here that I need to solve for apparent magnitude. This is how bright Aldebaran's going to appear in the sky, based on the fact that, this is how bright it really is. It's burning a bunch of, not burning, right, but it's fusing a bunch of hydrogen, producing a huge amount of energy, right, that we know, has this huge, very strong dependence on temperature. So it's hot, so maybe it's really bright. So, but how bright does it appear in the sky? Well, let's see. Okay, so apparent magnitude, which is like, really, think of that as how bright, when you look up at the sky and you notice that some dots are brighter than others, this is a number that represents that. Okay. Now, of course, the brightest things we see in the sky aren't stars at all. They're the planets. They're often the brightest thing. Other than the moon itself and the sun, they're by far the brightest. But anyway, we're calculating apparent magnitude. So the only thing I need to do to actually do some algebra would be to add mv to both sides. Okay. So a lot of times you're going to be adding a negative value. But here we're actually going to be adding a positive value to the other side. Okay, the reason that it has to be addition, right, is because it's subtraction here. So if I add mv, that would cancel it out on this side, and then all I'd end up with is a plus mv on the other side, on the right-hand side. Okay, so what that looks like is it would be 5 log times the d value that I saved divided by 10, so there's a 10 within the log, and then plus the absolute magnitude value I saved. Okay, so there we go. We have an apparent magnitude that we calculated for Aldebaran by referencing the table from the OpenStax textbook and the HR diagram. And that's exactly what you're going to do for Sirius. Okay. Now you're going to go on to another little figure, okay, which is one that I like to use. It's actually from a different textbook, but I stole it. Now we're going to consider Sirius's place on the following table. So this table isn't, as fundamental by any means as the HR diagram, but it does relate to Earth's, sky. When you look up at night, what are the things you can see? So we can see there's kind of some fun information here. We can see that we have at a very, large in magnitude, but very negative number, the full moon, okay, which, if these are all objects in the night sky, right, which of these appears the brightest? It's got to be the full moon, right? It has an apparent magnitude of about -13, okay, or about -12.5, really, because it's kind of right halfway between -10 and -15. By the way, this is a linear scale, okay? These are all apparent magnitude values like the one we just calculated. Okay, they don't have units, by the way. Apparent magnitude is a unitless quantity. Okay, it's just representing, it's just a ratio. And the reason we know it's unitless, by the way, it's also true of absolute magnitude. The name kind of hints at the fact that it doesn't have units. And that's also because if you look inside the logarithm, that d was measured in parsecs, okay? And I said that it was related to this idea of viewing the star from a fixed distance of 10 parsecs. Well, that's what the 10 is. So if we were actually to put units in here, we'd have parsecs in front of the d and also parsecs in front of the 10. So they'd cancel because they're in the numerator and the denominator. So you're left with a unitless quantity. And that's what you have to have. It's physically incorrect to ever raise e or any exponent to the power of something that has units, or take the logarithm of anything that has units, because that has no meaning. So you have to have something like a ratio like this. Okay? But anyway, going back to objects we see in the sky, we got Venus, which at its brightest is basically the brightest thing we can see in the sky, although Mercury gives it a run for its money, which is not included here, right? Because it's actually really hard to see Mercury. You can only see it just after sunset, or more likely just before sunrise, because the way it's, basically always near the sun from our point of view, being an interior planet at all. Jupiter and Mars at their brightest, when we're closest to them in our relative orbits, can also appear pretty darn bright, okay? So they can have apparent magnitudes that are in the negative. In terms of actual stars that are so bright that they have a negative apparent magnitude, Sirius is pretty unique. Okay, Alpha Centauri is up there as well. It has an apparent magnitude right around 0, which is funny to think that that's a number you can have, and that just means that you're actually a fairly bright object in the sky. Betelgeuse is also quite a bright star, as is Polaris, known as the North Star. All right, but we're getting in the dimmer category. We can see here that at a apparent magnitude of about 6, so going well into the positive range now, we have the faintest object that's visible with the unaided eye, right? So of the thousands of stars you can see on a really clear night without any, like light pollution, you're way out in the wilderness somewhere and there's not a lot of moisture in the sky, then the faintest thing you can possibly see is going to have that apparent magnitude. Okay, those are the faintest little stars. Now, if you get binoculars or a telescope, you can improve that number, right? So with a pair of binoculars, you can see things up to an apparent magnitude of 10. So it reveals a bunch of otherwise hidden stars, including a Bernard star, which is famous for its the fact that it has like noticeable movement. We can actually see it move through the sky. So it's kind of famous for that. With a small kind of Hobby telescope, right? We see what the range is, all the way up to like Hubble and Keck telescopes, the most powerful telescopes, and they can see objects that are as faint as having an apparent magnitude of 30, okay? Which you could never see with the unaided eye, the naked eye, right? Okay, so here I ask about some understanding of this very figure, such as, does a negative apparent magnitude mean the object is bright or dim? Okay, well, I kind of gave that away, so hopefully you're able to interpret that and give your answer down below. Okay, so moving on, question 6, what is the difference in apparent magnitude of Sirius and the full moon? Okay, so that's just reading them off the chart here, right? So you're just going to read where Sirius is, read the full moon, tell me the difference between them, okay? You can write it out as a sentence if you want, so you make sure you're answering the question the way I want it answered. Then you're actually going to take a ratio, because I asked here, does the apparent magnitude difference you found between Sirius and the full moon mean that Sirius is brighter or dimmer than the full moon, right? Well, reason that out, okay, and make sure that you're okay with what the negative means with the apparent magnitude, because they're both negative values, right? Do you think that the apparent magnitude relates directly to how bright an object object is in the sky? In other words, does the ratio m over moon over m over Sirius directly relate to the ratio of brightness? Like, what I'm asking here is like, so if you think about the numbers, right? Sirius is about, negative, let's say -2, right? And then I said that the full moon is -12.5. Well, then the ratio over here, moon to Sirius, would be 12.5 over 2. Does that mean that the moon is 6 times brighter than the star Sirius? Does that sound right? What do you think? Okay. Well, here, I give it away. It's not. It's another logarithmic scale. Okay. Like I said, logarithms are popular with astronomers for good reason. Okay, so in fact, what you're seeing, the difference between any two apparent brightnesses, okay, so that's what this is, apparent magnitudes, although sometimes you hear them called apparent brightness, but what the difference between those apparent magnitudes, it actually is not related to the intensity, how bright that little dot is in the sky, not linearly, okay, but instead logarithmically. So I'll read that out in the sentence, okay? So it says here, in fact, apparent magnitude is another logarithmic scale, so that'd be comparing between two apparent magnitudes. Notice, right, that if this looks a lot like the previous equation, and you think I'm repeating myself, notice that here we're comparing between two apparent magnitudes, whereas up with question 4, we compare between apparent and absolute, okay? Similar looking formulas, yes, but one has distance in it, okay? Okay, the other has a ratio of intensities, which I'll talk about in just a second. Okay, so they're different things, just similar looking formulas. Okay, so here we're going to compare between two apparent magnitudes. All right, so as I was saying, it's a logarithmic scale, and small changes in apparent magnitude, right? So even just going from like -1 to -2 are equivalent to very large changes in brightness. Okay, and I put brightness in quotes here in italics, because I want us to think of what is brightness. Okay, well, brightness isn't just some abstract idea; it can be quantified as energy per area per time. It's flux, right? Back that we saw of Stefan Boltzmann, right? But here, of course, the brightness is more like how bright the little dots appear in the sky. So it's almost like it's, so there, don't think of it in terms of, temperature, don't think of it in terms of distance. It's imagine that, all the objects we see in the sky are these, kind of little effective dots that are giving passing a certain amount of energy to our eyes, okay? And the brighter ones, like the moon, give us more energy coming into our eyes, coming into our retinas, getting picked up, by our eyes. Okay, so those units of intensity, okay, which can also be called, as I said, it goes by many names. Sometimes it's just outright called brightness. Sometimes called flux, as we saw before, or radiant flux. Also can be called irradiance. That's another one you see a lot. So it goes by many names, but it always has the same units: watts per square meter. Okay. And the mathematical relationship between apparent magnitudes, right, comparing any two, and their intensity is given by this formula right here. So now we're going to use that formula to compare the actual, values in intensity, how bright are our eyes picking up these objects, based on their apparent magnitude. So you can compare the moon to Sirius, okay? And then you're basically going to be done with Sirius, because the next question refers to Betelgeuse, which is, as I said before, bringing it back to the HR diagram after our little mathematical tangent, right? But hopefully one that really helps you understand those key terms introduced way back in question 1 a little bit more thoroughly, okay? But let's do an example, right? But not give away Sirius and the full moon. So let's choose two other things from our apparent magnitude table up here, our little figure. Let's go ahead and compare a couple of other bright stars in the sky. Let's compare Polaris to Alpha Centauri, right? These are stars that, might be easy to find in the sky, might be fun to find. So let's figure out how we could compare them. So I'm going to put down two apparent magnitude values. I'm going to give them subscripts that kind of are indicative of their names. So we'll have Pol for Polaris, and just kind of estimating it off of the chart, because there's not any finer tick marks here, but it looks like it's about halfway between 0 and 5, so I'm going to give it a 2.5, and that's the kind of estimate obviously I want you to do for Sirius and the moon in terms of their apparent magnitudes read off this table. You could obviously look them up online and find more exact values as well. Okay, and now let's do Alpha Centauri. That's flatly at 0, so that's fun. All right, so we'll just call this one. Look, I can actually call this one Alpha, although it won't let me do a subscript of a Greek letter. So anyway, we'll do ALPH. Okay, Alph, and that one is just 0. Okay, so then we're going to take those values and go back down here to calculate their ratio of intensities. Okay. So we just want the ratio. So just like here, for example, I say, how much more intense. So since you essentially have two unknowns here, if you're thinking, just solving for something, well, you can't solve for both of them simultaneously. So when I say how much more intense, I actually want I1 over I2. Okay, so I want it exactly as written as a ratio of intensities. Okay, so in this case, I'm going to be solving for, let's see, so the brighter one is alpha, so that's the one I'll put first. I'd recommend putting the moon as your M1, and so then I'm going to solve for the intensity of the brighter object over the intensity of the other. So what I'm going to be solving for is that difference. So we're going to call it our I, ratio. Okay, that's what we're going to solve for. But, how do we actually solve for it? Well, we have to rearrange this, right? So I'd have to divide both sides by negative 2.5. So I put over here, I'm going to kind of explain the steps and then put them over in Desmos. But here, I'll make this a little bit skinnier so you can see it. It's not cut off. So I'm going to have, like I said, M alpha. All right, so M alpha minus M pole. All right, so far so good. All right, and then all of that I'm going to divide by, you can put in parentheses as well, but I'm going to divide by negative 2.5. I don't need to because it's all up separately in the numerator. Okay, so far I've isolated everything, except for that ratio and the log. So how do you undo a logarithm, right? Because we have to do the inverse of the logarithm. Well, logarithms, when they're written like this, are base 10. Now, a natural logarithm is written as ln, and that's base e, where e is a special number, kind of like pi. It's what's known as a transcendental number, and very important to fields of math like calculus. But here, we don't care about that. We care about base 10 logarithms. So to undo the log, I have to raise everything that I've isolated over. Imagine isolating it over here on the left. I have to raise it to the power of 10. So I would take 10, all right, and then I'd raise it to the power of 10. Sorry, that's a wrong way to say it. I have to make it the power of base 10. So I have to raise 10 to that value. Okay, because right now, for example, right, you can see numerically this number over here. It's trying to graph it. I must have entered something. Because I don't have it uppercase P. There we go. So it has a value of 1. Okay, so that means what's going on here, right? That's actually that's useful. I like that. So it makes sense too because the 2.5. I should have thought of that. So that means, right, that right now that's telling me that my ratio of intensities is 1, but it's not really, right? In fact, I have to take 10 and raise it to that value. In this case, raising it to the power of 1. Well, anything raised to the power of 1 is just itself. So we definitely know what to expect. So if I raise 10 to this value, I'm going to cut and paste it. Cut it over there, put it in the exponent of the 10, then I have that the ratio of intensities of my chosen objects from the table of Polaris and Alpha Centauri, 2 visible stars in the night sky, is 10. Okay? Their difference, their apparent magnitude difference numerically was 2.5, but their ratio of intensities is 10. In other words, Alpha Centauri is 10 times brighter than Polaris. Okay? So that's the idea, logarithmic scale of how bright things appear in the sky. All right, so now let's look at Betelgeuse and finally bring it back to the HR diagram, because after all, that's the name of the lab, okay? But, these are the axes on the HR diagram, so we got to get into them if the HR diagram is going to make more sense to you. So now let's relate apparent magnitude back to the HR diagram by considering the star Betelgeuse. First, find the apparent magnitude of Betelgeuse. Second, find the absolute magnitude of Betelgeuse from the HR diagram and use these two values to calculate the distance. Okay, so that seems very similar to what we were asked, say, maybe back in question 4, but we're going to take 2 pieces of information, both off the HR diagram, and then, relate it back, okay? So, right, actually, 1 off the HR diagram, 1 off the table up above, which was, we'll say that's the table in question 5, okay? So let's take an example of that, although I don't want to do it with, obviously don't want to do your work for you, so I'm going to do it with a different star, but I want it to be one that's on, you can do it with Aldebaran, all right. We already know the distance to Aldebaran, so we could sort of confirm it, in a sense, although it might be fun to do one that's brand new. So let's actually go take a look at the HR diagram. What's a star that we haven't done that we could... let's see, Antares could be fun, although that's really close to Betelgeuse. So Mira, right? Because I don't need this to be one of the ones that's in that appendix of OpenStax because we don't need to know the distance. We're going to calculate it. Now, if you want to check your work, you could certainly look up the distance to Mira, and or we could even see if it happens to be one of the 20 brightest stars, right? Is Mira on the list? Vega, Altair, Spica, and Terry's is, right? That doesn't look like it. So it's probably, I think it's probably just included here because it's on the very high end of giants. So it's sort of famous in terms of an evolution of star point of view, but not so much in terms of being a bright star in the sky. So yeah, let's just do it. Let's find the distance to Mira using information off of our figures. Okay. So first of all, I'm going to read off the absolute magnitude of Mira off the table. Okay, I'm going to get Desmos open so I can enter it once I get the value. I'm going to use the same thing where I'm going to use this grab tool or selection tool to draw a horizontal line and see where it shows up on the left vertical axis, because I don't care about luminosity here, right? Because by the way, luminosity, right? So this is actually would be measurements of intensity, okay? Because that's the idea of luminosity. It is energy, right? Which I kind of mentioned in passing, but I want to be clear on that. But it's not going to be in units of watts per square meter because it's all multiples of the sun's luminosity. So moving over here, we're going to have a value for Mira. It's about halfway between 0 and -2 on a linear scale. So I'm going to say it's -1. Oh, it's a little bit bigger than -1. Let's do -1.2. Yeah, that could work. Yep, -1.2. Okay. So let's put this down. So we have M, and for Mira, okay, and that's going to be -1.2. Okay, so that's its apparent magnitude. So if you happen to be 10 parsecs from Mira, that's how bright it would appear. In fact, that would be the Mira's apparent magnitude for you at 10 parsecs from Mira. But we're not 10 parsecs from Mira, so we can go down and find it over here. All right, so let's see. Oh, but I wasn't thinking, because Mira is not on this one. I need one that's on both of them. So, okay, in that case, let's do, is Polaris on both the tables? Probably not. Okay, well, let's check again. Alpha Centauri might be. We have, there we go, Barnard Star, perfect, look at that. And Proxima Centauri is on there, which is pretty, actually pretty similar to Alpha Centauri, although Alpha Centauri I think might be significantly brighter. So we'll do one that is on both. Barnard Star. Okay, so we're reassessing here. We're gonna get a value for the absolute magnitude of Barnard Star, not Bernard Star, but Barnard Star. So I'll just put this as Barn. So I couldn't choose a Mira because it wasn't on both figures. Okay. And I need to be able to cross-reference them essentially. And that's going to be, I lost it. There we go. Try again. So halfway between 12 and 14. So 13. How is that? In interest of time, just do a quick estimate on 13. Positive now because it's not as bright. Okay. And then reading off the apparent magnitude for us here on Earth, it's actually going to be brighter. So that's kind of cool. Maybe you can tell what that's going to tell us about Barnard Star. So I'm gonna guesstimate 9. Okay, so M, again same subscript, BARN, is going to be 9. Okay. So then, how do I use those to calculate distance? Right? I use this formula up here. Okay. So in question 9, okay, you are doing something similar to question 4. In fact, more similar to in question 8, because you're literally using the same formula. But instead of knowing distance, you're going to solve for distance. So in the same way that we had to undo the logarithm up here in order to solve for the ratio of intensities, we're going to undo the logarithm to solve for d. Okay, and we're going to solve for the actual distance to Barnard Star. Okay, now what's cool is we can tell that it's actually going to be closer than 10 parsecs, because that's the only way that it could appear to have a lower absolute magnitude at 10 parsecs than it does on Earth. Okay, so Barnard Star must be closer to us than 10 parsecs. Okay, and if you don't quite follow me on that reasoning, you'll see how it works out here with the calculation, and the calculation will then give you that background of how to understand the reasoning. Okay, so same sort of thing. We're going to solve for d. Okay, I'm going to explain kind of how I would do it. I would take the difference of the apparent and absolute. So in this case, it would be M barn minus big M barn. Okay, so all right, uppercase. Okay, all right. So that's just apparent minus absolute, both magnitudes. Okay, and then we'll divide that by 5 because that's the value that's right in front of the logarithm. Okay, whereas before it was -2.5 of the other formula, different kind of leading coefficient there. And then that value, -0.8, that will be the power that we raise 10 to. All right. So the last step then is I would take 10, do a superscript, right? Basically, which is going to be a power. I do that by clicking Shift 6, the little caret looking symbol, and that's going to leave an open spot here. Obviously, also it's a common symbol on graphing calculators. It looks like it's the Shift 6, right? It's a little symbol above the 6 on a keyboard. Okay, and I'll put it there. Oh, I meant to cut it, not copy it. But there we got it. Okay, so we have a distance to Barnard Star of 0.158 parsecs. Okay, so 0.158. Not quite, because there's one more step. I'm like, oh, that's too close, right? Because there's one more step, because we've undone it, right? We've isolated everything, but there's still, unlike with the last formula, there's still a 10 that was inside the logarithm. So that means that when we did all this, this would still be d over 10, okay? So then what I have to do is actually, to get the d all by itself, I have to multiply by 10. So I got one more 10 in front, okay? So it ends up being 1.58 parsecs, okay? That is the distance to Barnard Star. If you want it in light years, you could just take it and take that value and multiply it by 1.36. All right. So I already have a value here. I'm going to call it uppercase D, so I don't duplicate my variables. Otherwise, I can't do anything with them in further calculations. But I could then, to convert it to light years, I could do 3.26 times that value, and that tells me that Barnard Star is 5.17 approximately by rounding light years from Earth. Okay. All right, so definitely closer than 10 parsecs. It's one of our nearby stars, but not the closest. The closest is about 1 parsec away, which is only about so I think it ends up being about 3.5 light years. That is the closest star there is, which is Alpha Proxima, which is actually part of a 3-star system. So there's three stars all orbiting, it's like sharing a common center of mass, which are quite common throughout the cosmos, throughout our own galaxy. We of course don't have that. Our sun does not have a companion; it's all by itself. But a lot of star systems, they are binary, or in the case of our closest neighbor, trinary, I guess, 3 stars. I think that's the term. Okay, so finally done with number 9, or at least an example of it. Now we're going to return to the HR diagram in earnest, less calculations and more interpretation. We're going to go back. Let's go back to the interactive one, okay, which is the link here. So you can see, indeed, it takes you right there. All right. Or maybe like me, you already have it open, so you can just tab over to it. So I have a number of questions here. I say, that you're going to select some settings of the showing only the brightest stars, and then you're going to then also show only the closest stars. Well, how do you do that? Well, you click over here. So you can. There are some basically things you can do. Some of these is kind of an older website. I'm not sure if these background exercises still work anymore. But what does work are choosing brightest and closest. So the default is none, doesn't show anything, and that's what we've seen so far. I haven't shown you this, but if I go and I click on the brightest, this will show little blue dots that reference or just display the location of the brightest stars in Earth's night sky. So the type of objects that would show up in a diagram or a figure like this one, right? This of course only shows a very select few, but this one is showing, I think, about 50 of the brightest stars in the night sky. Okay, I believe all 50 of them are visible with the naked eye. Right? Yeah, because there's at least 50 that are visible with the naked eye, so they must be, right? So these are the 50. Yeah, absolutely, the 50 brightest stars in the sky. Okay, and where are they located? Right? Well, a lot of them seem to be located on this thing called the main sequence, so kind of right down this main strip. There's a big group of them located up here. You can kind of have some fun and explore around, right? Kind of see what happens, because if you overlay this, this movable, customizable interactive dot on top of them, that's actually showing you kind of what that star would look like. So you can find out if these bright stars in the sky, if you could get close enough to them, are they big and red, right? Like some of them, or are they, middle-sized and sort of blue, or, pretty big and purple, right? Pretty big and violet, So, right, that's the idea. And here, you're then asked to classify them, right? So I say, what percentage of the brightest stars are cooler than the sun? So that's just going to be just thinking about temperature, right? So I bet you can kind of get an idea of that right away. Then what percentage of the closest stars are cooler than the sun? Well, let's go ahead and change the plot over to closest. All right. See, now the red dots are showing all the closest ones. That's interesting, isn't it? Right? Very different group of stars, isn't it? Okay. And then what percentage of the brightest stars are spectral class O or B? What percentage of the closest stars are spectral class O or B. So you see the difference here is brightest versus closest. And that's kind of the trend here with all parts of this. I asked the same question for brightest and closest on each of them. Okay. And then finally following up with what spectral class is the most common for the brightest and what spectral class is the most common for the closest. Okay. Now hold on. Where's spectral class? Well, spectral class was on that other HR diagram, so you could cross-reference them, but I think you might be able to change it over and show it with spectral class, although I'm not sure. Actually, this one might not have an ability to show spectral class. Let's see. Can we change the axis at all? Info, background. No. Yeah, that's like I said, there's not really anything there anymore. So let me actually click on this link again. Easiest way to get back to that. Plots, closest both, overlap, none. Yep, so the best way to do it is just to look at the temperature, especially because it's got that nice little arrow that shows up right there, so you can really get a very accurate idea of what the temperature is. So let's go ahead and turn back on the brightest, why not, right? So in terms of thinking about what spectral class they are, all you got to do is just then look at this HR diagram and then go back over to this one, because you can see, for example, that stars that have a temperature of 10,000. Actually, here I'll go up to our higher resolution one up here. So our stars that have a temperature of 10,000 are a spectral class of A. Okay. Similarly, stars that have a temperature around 30,000 Kelvin have a spectral class of B. Okay. If they're hotter than 30,000, they might be spectral class O right there. But that's how you would translate essentially from temperature right to spectral class, because it's just a direct idea. Spectral class is temperature. It doesn't give you any extra information. In fact, if you're wondering why have spectral class, it actually predates the understanding that they were temperatures, and we've just kind of stuck around with that naming convention. Okay, so that's what you're going to be doing there. So then when you're all done with question 10, it says, now a lot of these are basically concept questions, so I'll only really touch on these because I don't want to give too much away. A star that appears bright in the sky could be bright due to one of two reasons. Okay, cool. This is an important idea. One reason is that it is an average star that simply is very close, like Barnard star, right? Barnard star is one of our closest neighbors, right? Which is why it's pretty close, right? But was it really like an actual, super bright star? Was it its apparent magnitude on the upper end? No way, right? You saw, right, when we looked at it, right there, its apparent magnitude is actually really low. It's one of the dimmer, smaller, less bright types of stars that exist, okay? All right, so another reason, right, is that instead of just being one of our close neighbors, it could be so bright, right? It could be one of these super giants or one of these super hot ones in the main sequence that is just pumping out so much energy that it doesn't matter that it's far away, okay? So that's the idea, right? Comparing the two sets of the stars, brightest and closest, which reason explains why most of the brightest stars, those ones in the night sky, appear so bright? Is it because they're all the closest ones, okay? Or is it because they're all those like really big stars out there, right? That doesn't, they may be far away, but they're just so bright, okay? So you can definitely, because there's a clear answer to that. You just got to kind of think about what the data is telling you. Based on this line of thought, how common do you think very luminous stars are compared to the less luminous stars? Again, explain your reasoning, okay? Then, one of the tasks of scientists is to determine if there is a bias in the data. This may occur if a group of objects is chosen based on a certain property. An example of this would be if we were trying to find the height of a typical person, but bias our data by only choosing to measure the heights of basketball players, which of course are going to be a taller group of people, right? So that would be a bad choice of sample. Okay, maybe you've heard that if you've ever taken a statistics class. Okay, so that idea certainly applies to science, right? So do we have a bias, right? In the astronomical example above, one group of stars was chosen because they were the closest, the other because they were the brightest. Which set of stars, closest or brightest, is the least biased sample and best representative of a group of typical stars? Think about that one carefully. Okay, then. Since we kind of started early on with the Stefan-Boltzmann law, it was one of our key terms, and we revisited sort of a numerical approach to all of our other key terms like apparent magnitude and absolute magnitude. We're going to wrap this lab and kind of bring it all together, doing that with the Stefan-Boltzmann law. So here I say a magnitude, luminosity, and spectral temperature are the axes of the HR diagram, the horizontal ones. They are easily seen by a glance at the diagram. I've mentioned them many times. Other physical properties of stars are more difficult to ascertain. Okay, so like what they're made out of, for example, or what type of fusion is going on inside of them. Scientists have more or less found a way, but it's taken a lot of work. Okay, however, there is one more pretty simple idea we can come up with. And that is the size of a spherical object radiating light, because it is related simply to temperature and luminosity. one can use the HR diagram to determine the size of a star. This technique depends on the Stefan-Boltzmann law. Okay. Now here we actually see a more complete version of the Stefan-Boltzmann law that doesn't just have the sigma and the temperature to the fourth. It also has the surface area of a sphere. All right, and that's pretty great because that's going to give us, and also actually, it's the reason that there's two versions is because going way back over to here, they're not contradicting each other actually, because here this was flux, okay, and then here this is luminosity, okay, and I may have actually said that because those ones aren't strictly equivalent, whereas radiance and flux are. Luminosity is a bit different because luminosity you don't divide by the area. Okay, so flux was right here. You can see, right? It was, it has those units of its intensity. So as I guess it doesn't say it here, but I told you it has units of watts per square meter. Said it many times. Okay, but luminosity would just have units of watts. So when you talk about a light bulb, right? You talk about its wattage. That's luminosity. So you haven't divided by the area. You haven't sort of eliminated the effect of the area. And a lot of times you want to normalize or eliminate the effect of the area so you can compare between two things, and you don't care that the brighter object is also bigger, you just care that it's brighter. That's when you'd want to talk about flux because you've divided by area. But in this case, we actually want to find area. So we're going back to wattage. Okay, so luminosity is wattage, and it has the surface area of a sphere right in the formula because that's what we're trying to solve for. Okay. So the idea then is if you go back to the interactive HR diagram over here, we're actually going to be able to get an idea of why it is that when I move up towards these stars that are both, more intense in terms of their light and lower in temperature, it gets so much bigger, right? Why is it that in order to have a star that has, a luminosity of 230,000 times the luminosity of the sun, which is a real thing. There are stars that are 1,000,000 times brighter than our sun. That's crazy, isn't it, right? But to have a star that's 230,000 times more luminous, so that 230,000 times the wattage of our sun, okay? Well, that would require that that particular star has a radius that's 2,400 times the radius of our sun, okay? At this temperature of about 2,400 Kelvin, okay? So that's interesting, right? So that's telling me that for this fairly cool star, it would have to be huge, 2,400 times as big across as our sun in order to be that much brighter, okay? That much higher wattage. On the other hand, if I wanted basically that same, relative luminosity, so I wanted to find a star that was 230,000 times brighter than our sun, so 230,000 times the wattage of our sun, but I was going to find it instead on the very hot side of the stars, so basically way over on the left of the figure. Well, then I'd pull it over here, and it doesn't have to be nearly as big. It's still bigger, okay, but only 15 times bigger than the sun. Wow, okay? So that's really interesting. That's because when you're a much hotter star, because that's where we are on the far left of the figure, you don't have to be as big to be as bright. When you're a cooler star, you have to be really big to be as bright, okay? Because both, sheer size, because you have more area, pumping out light, and heat are going to make things brighter. But which one's more effective in making things brighter? Heat, by far. In fact, it's the difference between a square relationship, R squared, and a power 4 relationship, temperature to the fourth, okay? So you're going to use this law, this version of the Stefan-Boltzmann law, to find the size and solar radii of Aldebaran. See, that was a star we talked about a little bit, but I never talked about the size. So you're going to find the size, right? And you can you can get an idea, right? Because we could real fast go back over, scroll up to. We're almost done to the HR diagram. Look at Aldebaran, so we can kind of see it's in the giant category off of. So it's going to be somewhere kind of around here because there's no labeled stars in this one. But I guess somewhere probably right about there. Actually, probably it is going to be one of the brightest. So I'm going to guess it's that one. Just kind of a random guess, educated guess, I would say. All right, and then we're going to go. Then we're going to scroll down, right? Because this is if we think about it, right? So we want to then, think about its temperature and everything, and it's going to be obviously a fairly large star, as we can see, because it's fairly cool. All right. So that's the idea. You're gonna figure out how many solar radii it is, and if I was actually correct in guessing it, then I just gave away the answer. But you aren't just gonna just read it off. You're gonna let's see. So you're gonna find the size, okay, using the equation. Okay, that's why I left you space down here, because you're actually going to calculate it. You're going to read the temperature, okay, off of the graph, and then read the luminosity off of the graph, and then calculate the radius. Okay, because that's because you can read those values exactly on the labeled one, and that's the important thing. This one doesn't have any labels, so we're not sure that's Aldebaran. Whereas you can scroll up to this one, find the exact values of temperature, okay, and radius, and then exactly temperature and luminosity, okay, and then exactly calculate radius. Now it might happen that it is this one, and the value that you calculate is 53. In which case, hey, right, then I found the right one. By the way, the one time earlier when I did misspeak is when I said that this luminosity was the same as intensity. It's not. Luminosity is wattage. Intensity is wattage per square meter. That's the key difference. Very close, physical parameters, but different. Okay, so you're gonna do that twice. You'll do it with Aldebaran, then you're gonna do it with Betelgeuse as well. Okay, both of those you'll probably find are fairly large. In fact, you're going to find out that Betelgeuse is a supergiant, which is pretty cool. It's so big that it has a radius that's 214 times bigger than the radius of our sun. And it's not like our sun is very small, right? At least not by compared to planets, right? But it would be dwarfed by the size of Betelgeuse. And based on that information, how much larger is Betelgeuse than the orbit of Earth? Okay, well, you got to look up the fact. Okay, wait, never mind, I misspoke. So when you find Betelgeuse, you're going to find the answer. Okay, so you're going to find out how big Betelgeuse is. It's actually going to be some value bigger than 214. The reason is because then you're going to compare it to this ratio. Okay, because this is kind of like the ratio or the equivalence, the conversion I should have given you for parsecs to light years. Although again, you can easily look it up, right, or watch the video and see, watch this video and see that I mentioned it many times. But here, this is the conversion from astronomical units to solar radii. Okay, in other words, Earth is 214 times further from the sun than the size of the sun. Okay, but all that aside, right, we have that we're then going to have a value in astronomical units, in solar radii for the size of Betelgeuse. Then if you want to convert that astronomical units, just divide by 214. If you get a value for Betelgeuse in its radius that's bigger than 1 astronomical unit, that means that if we were to replace the sun with Betelgeuse, Betelgeuse would swallow up Mercury, Venus, and Earth. Like literally our orbits would be within Betelgeuse because it's that big, which means we wouldn't have orbits, right? Okay. On the other extreme are tiny stars like Sirius B, which is a white dwarf. Okay, that's the smallest type of star. Actually, isn't a star in the sense there's no more fusion going on, but it was a star. It's kind of the dead leftover core of a type of star. And we're going to use the Stefan-Boltzmann law yet again to find the radius of Sirius B, because Sirius B is one of the labeled ones, because I'm only asking for labeled ones you can exactly position. So there's Sirius B right there, same sort of thing. You're going to find its luminosity over here, and then find its temperature up here. So using those two axes, okay, top vertical, or top horizontal, and rightmost vertical. So then do the same calculation like you did for Aldebaran and Betelgeuse. Okay, but then find out how big Sirius B is, okay? And it's going to be small. And then compare it to the size of the Earth using another similar conversion, that this one, solar radius to Earth radii, okay? Instead of to astronomical units. And then finally, our last conceptual question, speculate on why you think some stars are so large while others are so small. Now, let's left this one kind of open-ended, but kind of put the best you can think of, or maybe what you know from other information. All right, well, thank you for watching this video. I'm sure it's been very informative, but also probably on the long side, but I hope it has helped you in working through this lab and enjoying this very interesting subject of the HR diagram. Bye for now.